Welcome to section 2.3, real zeros of a polynomial. In this section, what we're going to be doing is exploring some techniques we can use to help us find all of the real zeros of any polynomial function. Let's get started. All right, so the first process we're going to use is something called synthetic division. And this is a process we use to divide two polynomial functions by using the coefficients only. So if we look at our example here, we have a polynomial of ax cubed plus bx squared plus cx plus d. We're going to divide that by the factor of x minus k. And if you look at the way we set things up, we have a, b, c, and d with our box here, and we don't have any x values. And it's very specifically designed to help things become a little bit simpler and use just numbers and not variables. We're going to go through the basic process here, but initially, you're going to bring down your first term, and then whatever you bring down gets multiplied by what we're dividing by. So since I'm dividing by k, I'm going to multiply a times k to get ka, and then I'm going to add as I go down. This whole process is a little complicated, so we're going to look at doing this with some actual examples here, but we can see the basic framework here. The one thing I want to point out here too is at the very end, whatever number we get when we're done with the process is our remainder. And we can write our remainder as a fraction over what we're dividing by, but hopefully this becomes a zero, which will mean a lot more for us in the future. Okay, let's look at an actual example now. All right, here's our first example of synthetic division. What we're going to attempt to do is take a polynomial 3x squared plus 2x minus 1 and divide that by the factor of x minus 2. All right, if we look at our box here for our setup, notice we have a bunch of numbers. Let's talk about this 2 first. Your factor is going to help you identify what number goes on the outside, and what we basically do is solve that factor. And if I do solve that factor, what I would see is instead of x minus 2, I have a positive value of 2. Right? If I set this equal to 0, I would add 2 and I get my actual value. And so that's how those line up. When I look at my polynomial, I'm going to take the coefficients, so 3, 2, and negative 1, and that's what I will use to finish writing my box. See, we have the coefficients of our polynomial there. All right, let's look at our first step. Your first step is always to bring down the first number. In this case, it's a 3. So my 3 is going to come straight down, and I'm going to see it there at the very bottom. All right, now for our second step, whatever we get down here at the bottom is going to be multiplied by our outside value. So we're going to do 3 times 2, which is 6. You can see we have a 6 there. As we continue to go down, we're going to take these two values and we're going to add them. So 2 plus 6 is going to be 8. And we're going to continue our process. So just to reiterate, we add when we go down. Whatever we get, we multiply by our outside a value. So in this case, it's going to be 8 times 2. And if you multiply 8 times 2, then we get 16. And then we can see we're just going to add down again. Negative 1 plus 16 is going to be 15. So let's just kind of reiterate our process here. You add down, you multiply on the outside. Then you put your value. You add down, multiply by the outside, put your value, add down, and now we're done. And because that number isn't a 0, it's a remainder. So how do we take these values and rewrite our answer? Well, your answers here are always going to be 1 degree lower than what you started with. So we started with 3x squared. What's 1 degree lower than that? It's going to be just 3x. And this is going to be an 8. And then for our remainder, we're going to write that over our divider, which is the x minus 2. And we see we get 3x plus 8 plus 15 over x minus 2. Simple, right? All right, let's look at another example. All right, we're going to be dividing this, but we have a question here. First off, what are the coefficients, and do we see any missing terms? We always want to make sure that we're writing things in descending order so we don't mess anything up when we divide. And notice we have 4x cubed, and then we jump straight down to negative 13x, which means we are missing an x squared. Whenever we're missing terms, we have to represent them with something. So the question then becomes, how do we do that? Anytime we have a missing power within our polynomial, we're going to represent it with a 0. All right, so we got to make sure you put a 0 in. In this case, we didn't have an x squared, so we write that as a 0x squared. You cannot omit any power. Again, if it's not there, we're going to be representing it with a 0. Okay, now we can go ahead and try and do division with this polynomial. All right, we're going to go ahead and divide this polynomial by 3. A very important thing to note here is we are given a number, not a factor, which means we are already given a. So I'm going to take that number and write it directly on the outside. That's going to be my a value. Now I'm going to write the coefficients for each one of my terms. We have 4x cubed, 0x squared, negative 13x, and then positive 10. All right, I'm going to go ahead and just bring this 4 straight down because we're always adding down. And now I'm going to take my 4 and I'm going to multiply it by my a value. And 4 times 3 is going to be 12. And then once again, we're going to add down. So we have 0 plus 12, which is going to give me 12. And once I get my value, I'm going to multiply that by my a value. 12 times 3 is 36. If I go ahead and I add down one more time, negative 13 plus 36 is going to be 23. And then I'll take that 23 and I will multiply it by my a value, and I'm going to get 69. And last but not least, I'm going to go ahead and add straight down one more time. So 10 plus 69 gives me a final answer of 79, and that is my remainder. All right, when I want to write my answer, again, we're going to look at our initial degree, which is 4x cubed, and we're going to start with 1 degree less than that. So instead of 4x cubed, I'm going to have 4x squared, and then we'll go down 1 degree, so we get 12x, and if I go down one more time, I get 23. And then for my remainder, I write it over my factor. Now I was given an a value, so to convert to a factor, I just do x minus, which means I have x minus 3. So for my final answer, we have 4x squared plus 12x plus 23 plus 79 over x minus 3 as our result when we divide our polynomial by 3. All right, guys, time to check in and see how much this is making sense. What I would like for you to do is go ahead and do the synthetic division, dividing the polynomial by 6, and select the correct remainder. So from the possible answers, which one is correct? And then check back in and see how you did. Okay, so no, I'm given my a value because I'm dividing directly by 6. So I'm going to go ahead and write that on the outside. And then I'll fill in my coefficients. We have 2x cubed minus 9x squared minus 16x plus 12. So we're not missing any terms. All right, our pattern is to add down and then multiply. So I'm going to add the 2 down. Multiply 2 times 6 to get 12. If I add down, I get a positive 3. 3 times 6 is 18. If I add down one more time, I get a positive 2. And then 2 times 6 is 12. And finally, 12 plus 12 is 24. So my remainder then is going to be 24. If I'm going to go ahead and write down my answer, once again, we look at our initial degree, which is 2x cubed. And we're going to go ahead and go 1 degree less than that. So instead of 2x cubed, I have 2x squared. And when I go down one more degree, I have plus 3x. And then plus 2. And finally, we're going to write our remainder over a factor. So since my a value was 6, I'm going to say it's going to be x minus 6. And there's our final answer. All right, for our remainder theorem, the remainder of a division of a polynomial of f of x by x minus k, so once we finish doing synthetic division, is always going to be the same as f of k. So what does that mean? Well, what that's telling us is, if we look at our example here, we've done our synthetic division, we got a remainder of 68, and we were dividing the whole thing by x minus 3. And what that tells me is, if I were to just take 3 and plug it into my equation initially, I would get 68. So a remainder is always going to help us figure out kind of an ordered pair. If I look at this, I plugged in 3 to my function, I got out 68, and again 68 was our remainder. So it's kind of helping us pair up x and y values. It's kind of a neat trick, and we can always use this to check to make sure we've done things correctly. If for whatever reason we got a remainder that didn't work, for example, let's say you did the math and somehow you got 70. Well, if I were to plug in 3 into my equation, I should get 70. But we can see that we actually don't get 70. We do, in fact, get 68. So it's a way for you to check your work and make sure you've done things correctly. All right, for our factor theorem, this is kind of the main purpose of doing synthetic division, is we want to use it to help us figure out factors. So we can see that a polynomial has a factor of x minus k if f of k equals 0. And looking at our examples, what that means is you've done your synthetic division and you end up getting a 0 as your last value. And what that tells you is that the number you're dividing by is not just any number, it's actually a factor. So since I'm dividing by -2 and I got a 0, a factor of x plus 2 is going to be a solution or an x-intercept for our function. If you look at the second one, again, we divided by 1, we got a 0, so then that means x minus 1 is also going to be a factor, a solution, or an x-intercept to our function, whatever you want to call it. And then we can go ahead and use that to help us completely factor our actual polynomial. So our first factor was x plus 2, our second factor was x minus 1, And then if I look at this 2 minus 1, that's how I get my last factor of 2x minus 1. When we are not given specific values to use for synthetic division, we're going to be applying our rational root test. And what that tells us is all the possible numbers we could use to help us do synthetic division. The way we're going to do that is we're going to take the factors of the constant term, which is generally your last term if it's in descending order, and we're going to divide them by the factors of your leading coefficient, which is generally going to be your first term. And we end up getting a lot of expressions that look kind of like this, a sub 0 over a sub n. Let's go ahead and look at an example of this to help us identify the possible values we could use for synthetic division. All right, we're going to go ahead and try and find the possible rational zeros for our polynomial by using our rational root test. In order to do that, we're going to identify our leading coefficient and our constant. So our leading coefficient is going to be 2, and our constant is going to be 3. Again, because it's in descending order, it's pretty quick to pick that out. And I want to look at what are my factors of 3? Well, I know that 1 times 3 is going to equal 3. I also know that negative 1 times negative 3 is going to equal 3. So those are all my factors of my constant. For my leading coefficient, I have 2, so 1 times 2 is going to be 2. And then negative 1 times negative 2 is going to be 2. All right, so what I need to do now is take these values and just kind of simplify them. I have, for example, let's look at the 1. So I can do 1 over 1, which results in just 1. Or I could do 1 over 2, which results in 1/2. We're going to continue this process, and I'm going to divide 1 by all of my values in the denominator. So if I divide 1 by negative 1, I get negative 1. And if I divide 1 by negative 2, I get negative 1/2. So I know that I have a positive and negative 1, and I also have a positive and negative 1/2. Unfortunately, we get to repeat this with all of our values in our numerator. So I'll be dividing 3 by all of my numbers in my denominator, negative 1, and then also negative 3. Let's go ahead and do the positive 3. If I divide positive 3 by 1, then we get 3. If I divide positive 3 by 2, we get 3/2. And then if I divide 3 by negative 1 or negative 2, we end up just getting positive or negative 3, and then positive or negative 3/2. Fortunately, I don't have to do the negative 1 because I'll just repeat what I had with my first two possibilities. I also won't need to repeat the negative 3 because, again, I'll repeat what I have here. So in total, I have 8 different values I could use to do synthetic division, and I know that they are the right ones to do if I end up with the remainder of 0 as my final value. All right, we're going to try this one more time. We're going to try and find all of the possible zeros for our function x cubed minus 3x squared minus x plus 3. So we're going to take our factors of our constant, which is going to be 3, so plus or minus 1, and then plus or minus 3. And we'll divide those by the factors of our leading coefficient, which in this case are going to be 1, which gives us plus or minus 1. If I go ahead and divide my positive and negative 1 by my denominator, I end up with just plus or minus 1 as my possibility. So I have plus or minus 1 there. And if I divide my positive negative 3 by my denominator, again, get just positive negative 3. So this time I actually only have 4 values that we need to do with synthetic division to figure out which ones are the correct ones. Let's talk about an easier way to figure out the right ones to use. So sometimes we want to know all the possible ones. Sometimes we want to jump straight to the ones that actually work. And so what we're going to do is graph our function on a scientific calculator, maybe something like Desmos, and we're going to identify the zeros of our function. So we knew from the last example that we had some possibilities. We had positive and negative 1, and we also had positive and negative 3 to use as our options. If we look at our graph, we can see we have an x-intercept at negative 1, at positive 1, and at positive 3. And so what that tells me is those are the values I would use to help do synthetic division to completely factor out my polynomial. Descartes' rule of signs is something we use to figure out the number of positive real zeros and also the number of negative real zeros. And the way we do that is for our positive real zeros, we're going to look at the number of sign changes of your original function. And for the negative real zeros, we'll look at the number of sign changes of the function f of negative x. Let's go ahead and explore this with an example. All right, so we see that we have a polynomial 3x cubed minus 5x squared plus 6x minus 4. First thing we want to note is that this is in descending order, which again is very important for Descartes' rule of sign. I'm going to look at the sign changes of our function. So we start with something positive, and it switches to something negative, so that is going to be one sign change. And then we have a negative term that switches to a positive, which is going to be two sign changes. And last but not least, we're going to switch from something positive to something negative, which is now three sign changes. So what that's going to tell me is we're going to have 3 or 1 positive real zeros. The reason why we have to go down by 2 is to factor in the possibility of imaginary zeros, which we'll talk about later on in the chapter. Let's go ahead and evaluate our negative zeros. So what we're going to be doing is evaluating f of negative x. So I'm going to plug in a negative x everywhere we saw a positive x. I apologize for the end there. Okay, so if I simplify this, I'm going to have negative x cubed, and then a negative x squared, and then just negative x. So my final polynomial is going to be negative 3x cubed minus 5x squared minus 6x minus 4. So now if you look at our terms here, we see we have a negative to a negative to a negative to a negative. All of our terms are in fact negatives. There's no sign change, which means that we are going to have 0 negative zeros. All right, for our problem here, we're going to find all the real zeros. In order to do that, we need to kind of identify how to start, and we don't have any zeros given to us, so we can use our rational root test. So if we take all of the factors of our constant term and divide them by the factors of our first term, we see that we can get something like plus or minus 1, 2, 3, and 6, all over plus or minus 1 and 3. So we can go through and use those individually. I actually know which ones to use. If you didn't know, though, you could simplify that to get your possible values. So we do simplify. I believe we get plus or minus 1, plus or minus 3, plus or minus 2, plus or minus 2/3, plus or minus 6, and then plus or minus 2 again. Okay, so I'm going to go ahead and use some values here. We're going to start by doing synthetic division with a 2. I'm going to go ahead and write down my values. We have a 3, a 2, negative 19, and 6. I'm going to go ahead and go through this so we can get our answers here. Okay, we got a 0 at the end, so this is verifying that our 2 is actually one of our zeros. I'm going to go ahead and do it again to fully simplify this. I'm going to use negative 3 this time. And once again, we got a 0 at the very end, so whenever we're correct, I can go ahead and write this out as a factor if I needed to. We know we started with something to the third, so this would be to the second. This means this is going to be a linear factor, or to the first power. So I'm going to go ahead and add in some x's there. This would just be 3x minus 1. So for my zeros, we have x is equal to 2, x is equal to negative 3. And then I have to try and solve this. So I would actually just set that equal to 0. And when you solve that, you end up getting that x is equal to positive 1/3. And those are my 3 real zeros for this function. All right, one more example here. We have z to the 4th minus z cubed minus 2z minus 4. The orange is kind of hard there, so I went over this with black. We're going to go ahead and start the same way. I don't know what to use, so I'm going to list my possible zeros using the rational root test. So I would get plus or minus 1, plus or minus 2, and then plus or minus 4. And I'm dividing all those by 1, so those are essentially going to be my zeros. All right, we're going to go ahead and do synthetic division here. Again, if you didn't know, you could test your values until you got a 0. I do know which ones to use though, so we're going to start with a negative 1. And then we have 1, negative 1. I don't have a squared component, so I'm going to put a 0 for that. Negative 2, and then negative 4. I'm just going to go through the process of doing my synthetic division. We're going to be adding down and then multiplying on the outside. I'm going to go through this to get to our answer here. Okay, and you can see that I did in fact get a 0, so that verifies that negative 1 is one of our zeros. If we continue this process, I'm going to use a 2 now. So again, we're adding and multiplying. And one more time, I got a 0. Okay, so I know for sure that I have 2 zeros. I have a 0 at negative 1. I have a 0 at 2. What I need to do now is try and use what I have left to find my last zeros. Again, we start with something to the 4th power. So after my first synthetic division, this would be to the 3rd power. After doing it again, this is going to be to the second power. So I'm going to go ahead and just fill in the values. This is 1x squared plus 2. If I wanted to solve that, x squared plus 2 equals 0. I would end up getting x is equal to the square root, sorry, plus or minus the square root of -2, which is an imaginary 0, and we are trying to find all of the real zeros, so this doesn't actually help us. Which means we only have 2 real zeros. We have -1 and +2 as our real zeros. All right, guys, that does it for the notes. Go ahead and get started on the homework. Good luck.